Welcome back, everyone, to our next lesson. Our lesson today will be on chemical equations, our first lesson in our new Unit 8, which is all based around different types of reactions, how they're put together, different types. We'll look and see how we can balance equations. For today specifically, the I can statements that you want to be aware of, things that you should be able to do by the end of this lesson. You should be able to balance equations when given formulas for reactants and products. You should be able to write equations when given names of reactants and products, and you should be able to find the missing mass of a reactant or product when given the masses of the other remaining reactants and products. So if we have a missing one of those and we have the rest, we can figure out the missing mass. To start with, what is a chemical equation? Now, really, chemical equations are symbolic representations of a chemical reaction. They have to include certain different pieces here. We want to include what we call the reactants, which are the substances that are being reacted together. We want to include products, which are the substances that are being formed from the reactants. The phases of each of the substances that are involved, both reactant and product, how many moles of each substance that we have. And this last one here, the resultant energy change, is sometimes included, it is sometimes not. But we will often see this in there as well as a delta H value. Our general formula for a chemical equation is reactants yields products. I call this yields. You might see it as forms, produces, change. But that is the separator, the arrow there is a separator from reactants to products. We will add coefficients in front of our reactants and products to indicate our mole ratio of reactants to products, or how much of each we would essentially need. First one we'll look at here, first example of a chemical equation. Give you a second to kind of digest this. Feel free to pause the video. Make note here of the phases that we have. Our mole ratios, there's currently no numbers in front of any of our substances. The arrow separates reactants from products. So we'd have reactants, we'd have products. Now if we kind of read this equation out, it says that hydrochloric acid, HCl, reacts with zinc metal to form hydrogen gas and zinc chloride, which is an aqueous solution. The law of conservation of mass. What it says simply is that mass cannot be created or destroyed when we are talking about physical or chemical changes. We do have mass that is destroyed in a nuclear change, and this is what we call the mass defect, where we do destroy a small amount of mass to produce a rather large amount of energy. But within the law of conservation of mass, so with any physical or chemical change, whatever elements we find in our reactants are the only ones that can be found in the products. Nuclear change, we do have a change from, or can have a change from reactants to products. What we start with isn't always necessarily what we end with, but that's nuclear change. And we must have equal numbers of moles of these elements on both sides. So I want to make sure that the amount of stuff, whether that's mass or moles, is going to be the same on both sides of our reaction. So given our example again here, we can see that this equation as it's written is violating the law of conservation of mass. On the left-hand side here, we have 1 mole of hydrogen, but on the right, we have 2 moles. We have 1 mole of chlorine on the left, and we have 2 on the right. This is a violation of the law of conservation of mass. So in order to make this reaction work correctly, we have to balance the equation. So that'll give us equal numbers of elements on both sides. And in order to do this, what we have to do, the only thing we can adjust are the numbers coming in front, or our coefficients. So we can adjust these numbers in front here, which will help us to balance out the formulas coming after it. We can't change H2. We can't call H2 H1. It's not the same. Hydrogen gas is a diatomic element. When it's by itself, it is always formed diatomically with two hydrogen atoms bonded together. So we have to write it that way when it's by itself. We can't just change the subscript because changing the subscript will change what the actual formula is or what the substance is. So we can only adjust the coefficients in the front. Now those coefficients act as multipliers, basically telling us how much are we going to need of that substance. We can then factor that multiplier through, or factor that coefficient through, and multiply each of our elements accordingly. So when we do this, when it's balanced, the only thing we've added here is a 2 in front. So that's saying that we need 2 moles of hydrogen chloride, or hydrochloric acid, that react with 1 mole of zinc. So it's a 2-to-1 ratio of hydrochloric acid to zinc. Now if we check, our numbers should balance. 2 chlorines on each side and 2 hydrogens on each side. And the diatomic elements we're always going to want to balance as diatomic. Remember, those are our Brinkelhoff elements. So when you're writing chemical equations, first, write the formulas of the compounds. Sometimes we'll be starting these with names, so we've got to write these out. Otherwise, you'll be given the compounds. My advice to you, and you'll see how I do these, start in pencil, write coefficients one element at a time, deal with one thing first, and then see how the change affects everything else. To reiterate, we can only use coefficients. We cannot change chemical formulas in order to balance. We can't say H2 does not equal 2H. The last part here says revise when necessary. This will happen a lot. That's why we want to use pencil. You'll be doing a lot of revising. There's not a great technique to do this. It does take a little bit of practice to get used to it, but there's no real tried and true way of doing it the same way every single time. Remember the difference between coefficients and subscripts? The 2 in front of the Cl is a coefficient. The 2 after the Cl is a subscript. So the 2 in front means that there's 2 atoms of chlorine, whereas the 2 after the Cl means that we have 1 molecule of diatomic chlorine. That'll be true for any of our diatomic molecules. So if you see these in a reaction, they need to be written diatomically when they're by themselves. And this will make things a little bit more hairy in a compound like sodium chloride. It is a 1-to-1 ratio, but the chlorine, once it's separated, forms diatomically. So if we look at it just like this, yeah, that's balanced, 1-to-1 to 1-to-1. But chlorine has to be diatomic. So this is going to throw off our balancing. Because really what they should be is Cl2. Now we end up with 2 chlorines on the right and 1 on the left. That has to be remediated, so we're going to balance it. How could we do that? Well, the sodiums look good for now, 1 and 1 on each side of the arrow. For now it's balanced, that might change. So we have 1 chlorine on the left, 2 on the right, so we multiply that together. And that's going to give us the total that we need when the equation is balanced. So 2 times 1 gives us 2. We should have 2 chlorines on either side of the arrow when the reaction is balanced. So there's already 2 on the right, so we're good there. So we're going to put a 2 in front of the NaCl to give us 2 chlorines. Now that tells us we have 2 chlorines on each side, but now we have 2 sodiums on the left and 1 on the right. So that's going to throw out the balancing for sodium. You can see where the revision is going to be necessary. So now to adjust that, we put a 2 coefficient in front of the Na because 2Na is different than saying Na2. Those are not the same. If we go back and check, we have 2 sodiums and 2 chlorines on both sides. Now the reaction is balanced. I like to go through here and just kind of mark down. We have 2 sodiums, we have 2 chlorines, we have 2 sodiums and 2 chlorines. I like to write the numbers right above. And I'll do this again in another example, just to keep track of how many of each element that we have, because it'll certainly help. So in checking this, H2 plus O2 yields H2O. Now that I'm looking at this, phases are not included on this reaction. But we'll move on. There are 2 H's on the left. There are 2 on the left of oxygen. And on the right side of the reaction, there's 2 hydrogens and 1 oxygen. So we multiply 2 times 1 for the oxygen since they don't balance. And we get a factor of 2. So we should have 2 oxygens on both sides in order for it to be balanced. So the only way to adjust the water is to put a 2 in front of that formula. Now we have 2 hydrogens, 2 oxygens. 2 times 2 would be 4 hydrogens, and now we have our 2 oxygens. So oxygens are good here, but it messes up the balancing with hydrogen. So to remedy this, we'll put a 2 in front of the H2 on the left-hand side. 2 times 2 gives us 4. O2, there's 2 there. 2H2, that's 4, and 2O would be 2. Now we're left with 2 oxygens on both sides and 4 hydrogens on both sides. So now this equation is balanced. We'll try a little harder one. So again, I like to start with identifying how many we have here. That's 1. There's 2 oxygens, 2 aluminums, 3 oxygens. 1 aluminum on the left, 2 on the right. We multiply. There should be 2 of each on both sides. So we put a 2 in front of the aluminum. Now this will help us to balance. We have 2 there, 2 here, 2 here, 3 here. So we got to fix the oxygen. 2 on the left, 3 on the right. We multiply that. Each side should have 6 oxygens. So we're going to put a 3 in front of that O2 on the left-hand side here. When we do that, this number on top, I'm just going to cross that out, becomes a 6. And now we're going to have to do something else in order to get this to balance, because we have 6 oxygens now on the left and only 3 on the right. So we're going to have to put something in front of the Al2O3. So now to check that, we have 3 times 2 is 6, 2 times 3 is 6, 2 times 2 is 4, and we're left with 2 here. So you can kind of see this stepwise. Aluminum's now off, so we have to adjust this. If we change this number here, it's going to affect the oxygen. So if we deal with a substance that only has 1 species involved, it's a little bit easier to balance. So if we put a 4 in front of the aluminum, that's not going to affect anything else but the aluminum. We change that 2 to a 4. Now we're left with 4 aluminums, 6 oxygens, 4 aluminums, and 6 oxygens. Now this is balanced. So at this point you should be able to balance a chemical equation to show conservation of mass. We'll do lots of practice with that in class. The next step that you should be able to do is write an equation when given names. So instead of being given formulas, if you're just given names of a reaction or an equation, you should be able to convert those into a formula, the names into a formula, and then balance the reaction. So to start, we have magnesium and lead-4 nitrate yielding magnesium nitrate and lead. To do this, magnesium just by itself is going to be elemental magnesium, so its symbol would just be what the element is. Same is going to hold true for lead. It's not combined with anything, it's just the element as it is off the table. You guys know phases based off of their positioning on the table and standard temperature and pressure. Lead 4 nitrate. This is going to, depending how comfortable you are with this, since it's lead 4, it's going to be lead plus 4, and nitrate is a -1. We swap and drop. So we get lead 4 nitrate below, so we need 4 nitrates to balance the plus 4 lead. Magnesium plus 2 nitrate, NO3 -1. We swap and drop, and we get our equation. So we convert that over from words to formula. Now we can balance it. I like to treat these ternary formulas, treat the polyatomics as one whole item. So right now, well, this is balanced already. We got 2 magnesiums, 1 lead, and here we have 4 nitrates. The formula over here is 2, but we look at the 2 here, this will give us a total of 4 nitrates. So this is balanced with the 2 magnesium coefficients placed in front. Try it again. Feel free to pause this video and convert these over to symbols. Lead 2 nitrate plus sodium phosphate yields lead 2 phosphate and sodium nitrate. Putting that into a formula, we have this big huge mess, or it looks like a big huge mess, listed here. Start by checking your numbers. We start with 1 lead, 3 leads, 1 sodium, 3 sodiums, 1 phosphate. I'm going to treat that as 1 polyatomic. Over here we have 2 phosphates, and we have 1 nitrate, and here we have 2 nitrates. Any species by itself I would tend to leave towards the end, because those coefficients we can change and it's not going to affect anything else. So it's good to leave those till the end. This may take a fair amount of trial and error. But we can see with the 1 times 3 for the lead, we should have a total of 3 leads on each side. So to balance that, we put a 3 in front. I like to cross these out and adjust your numbers. We now have 6 nitrates. We can jump to anything that's that you feel like doing next. So we got lead, nitrate. We can do the nitrates. We balance the leads. We have 6 nitrates on the left. We have 1 on the right. 1 times 6 is 6, so we should have a 6 here. This gives us 6 sodiums, 6 nitrates. So now the nitrates are balanced with 6 and 6. I'm going to go with the sodium. 6 sodium on the right. There's currently 3 on the left-hand side. I'm going to put a 2 here. This becomes a 6. This becomes a 2. And our phosphates will balance, 2 and 2. So our mole ratio becomes 3 to 2 yields 1 to 6. And those are just the coefficients in front of each species. Remember, if it's blank, we assume it's a 1. Alright, at this point you should be able to convert names into formulas and then balance a chemical equation. Last thing we'll talk about today is about the missing mass. So in any chemical and physical reaction, mass of the reactants should equal the mass of the products. The law of conservation of mass states that we cannot create or destroy mass in any physical or chemical change, only a nuclear change. So a typical problem that you might see, we take 35 grams of nitrogen gas and react it with hydrogen gas to produce 42.5 grams of ammonia. How many grams of hydrogen gas were reacted? So let's think about this. We're trying to produce ammonia We have 42.5 grams of this. It's produced from nitrogen gas and hydrogen gas. We know we have 35 grams of this. So if the total ammonia is 42.5 grams, whatever this is plus the 35 has to equal 42.5. So we need 7.5 grams of hydrogen in order to make our 42.5 grams of ammonia. Let's try again. How many grams of aluminum are formed when 45 grams of aluminum oxide are decomposed into aluminum and 21.1 grams of oxygen? Keep in mind here, decomposed, broken down into. So we have here aluminum oxide. This formula here, aluminum oxide plus 3 oxygen minus 2, we swap and drop. We get Al2O3. How many grams of aluminum are formed when we decompose this aluminum oxide into its parts, aluminum and oxygen? Remember, oxygen is diatomic. We have to write it that way. This is 21.1 grams, and we started with 45 grams of aluminum oxide. We can subtract that value over, 21.1. 45 minus 21.1 gives us 23.9 grams of aluminum that are formed. What we want to try and do here is make sure the masses on the reactant side equal the masses of everything on the product side. Another example, how many grams of iron 2 sulfide must be decomposed to form 33 grams of iron and 19 grams of sulfur? So we left iron 2 sulfide, and that will be decomposed or broken down into its component elements of iron and sulfur. We know that we're left with 33 grams of iron and 19 grams of sulfur. What would be our starting amount of iron sulfide? We add those up. We must start with 52 grams of iron sulfide. So you should be able to apply the law of conservation of mass to determine the missing mass of a reactant or product in a chemical equation. The key there, making sure that masses on both sides for our reactants and products are going to equal each other. And again, this only applies to any chemical or physical reaction. Lots more to go over in class. Have a great day, everyone.